Hello everybody, welcome back. Today's lesson is going to be a little bit of a repeat. It's a nice chance for a refresher on quadratics. Now we've dealt with quadratics a lot during this semester because they are one of the first times that we get to really experience this idea of saying that we can talk about something in addition in the same way that we can talk about something in multiplication. In other words, sometimes we can throw a bunch of things into a pile, but when we're lucky, we can organize that pile in such a way that we have a nice row, a nice grid formation. And it also reminds us that we have the power that even if I can't organize it into a grid, I can always add a couple of elements in order to make it into a nice pretty square. And we're going to go back through that today and just kind of see how it is that we can have control over arithmetic with this idea, that we don't have to always just do things in a forward motion, but that we can have some creative fun with how we choose to, change our perspective in order to have that same meaning we're starting with look a little bit different and give us a lot more opportunities. So let's go ahead and take a look here. Now, possibly the number one reason why we solve quadratics or why we factor quadratics to assist us in solving is because of the zero product property. And this is pretty much saying that if we have something where we have this quadratic equal to 0, is it best for us to try to figure out when all of these things perfectly cancel each other out and try in different x values, like try plugging in a value of 1, see if that works, or 2, see if that works? Or if we make it look like multiplication, we just need to say, well, when either part is equal to 0, the whole thing is. And that's a much easier solution. Now, the interesting thing that I don't know that we always mention as well is that the problems don't even have to be well set up like this. Like, let's take, for example, a situation where I had 5x squared plus 3x plus 2 equals 6x squared plus 14. We can always take these kinds of problems, and if we just subtract 14 from both sides, and if we just subtract 6x from both sides, 6x squared from both sides, we can always just look at these as being the same things. Negative x squared plus 3x minus 12 equals 0. So we can always make them look into zeros and then use everything that we've been playing around with to be able to solve them out. So it's nice to just kind of keep in mind that we can always take anything that is quadratics on either side or parts of quadratics on either side, and we can always make it look like a quadratic equal to 0 and employ every single tool that we're about to practice here. But first, can we solve this equation by factoring? Let's try to remember a couple of different things that we have. First of all, these are called quadratics, and it might be a little bit weird to think, why is it that they're called quadratics? After all, there's only 3 things here, the 5, the 14, and the negative 3. At the very most, the x is just being squared, so why are we calling it a quadratic? A quad usually means 4. So where are we getting this idea of 4 from? And it's because as far back as quadratics were studied, or as far back as these questions were being analyzed, they were always being represented with rectangles. So we were going to recall for a moment that this 5x squared could be thought of as 5 of these x squares, 1, 2, 3, 4, and 5, 14 x blocks, 1 block, 2 blocks, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, and then 3 anti-blocks, 3 unit blocks that are actually made to be negative, so maybe we'll shade those in to keep that special. Now, all of this here, like we said, these are x squares because I have x times x gets me an x square. We don't know how big x is, but whatever it is, that's going to be the square formed by it. These are x blocks where I have x and then they're 1 unit large, so that gives me an inside area of x times 1 is just x. And here I have these negative areas, so they're almost like what would have normally been a 1 times 1 square is actually made opposite. So that means it's a 1 by negative 1 square. One of these sides has to be opposite. Now we're trying to organize all of this into a rectangle, and I'm going to show you what the rectangle is first before I show you how it is that we get it. Now here you have it exactly as I've organized it into a rectangle. And let me color this in a little bit just so we can trace exactly what happened where. We've got, I'll make these x squared blocks the orange. So we've got 1, 2, 3, 4, and 5. And so I put those down here. 1, 2, 3, 4, and 5. Pretty cool. Now I've got these x by 1 blocks. I'm going to shade these up in, let's do some light green. We'll use this. Now I've got those right here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And those appear right here. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, and 15, and 16. Oh wait, I only had 14 of them. Okay, that's no problem. In fact, actually one of these is a little bit extra. This one right here is actually an anti-X block that I had to create up here in order to make it actually fit into a rectangle. So I created an opposite X block, but in order to keep the same meaning, I made sure that in my picture, I also made a new X block to keep track of that one. So essentially I said that I was going to kind of need to go into debt by one X block, but that's okay. I'm going to kind of say I'm going to gain an X block and show that I'm in debt one X block. And so no problem. One of my X blocks helps fill in the 15 down here, and I keep track of the opposite block. And then I've got my 3 that are right here in the corner, my 3 units, my 3 anti-units. And I can go through and I can talk about what are the dimensions of this rectangle. After all, this is 5 x's long. Each of these was an x by x long. So I have an x plus an x plus an x plus an x plus an x, which gets me 5 total x's in length. And then over here, I've got one negative, one opposite length, a -1 length. So that's a 5x and a -1, no problem. And then I can look over here and I say, okay, well, again, this is an x by x squared. This was my x length right here. And then I had 3 normal groups. So I had a +1, a +1, and a +1 that got me 3 total. So I have +3 and an x. And what's really interesting is that we can actually look at this entire thing and say that this can be thought of as a 5x minus 1 by x plus 3 rectangle. And just to check out on that, let's see exactly how that would work. We'll do it in the picture version and we'll FOIL it out in the exact same way. So the picture version of trying to multiply this would say, no problem, I have 5x minus 1, and I would multiply that by x plus 3. And I would go through this entire thing and I'd say, okay, x times 5x gets me 5x squared. X times -1 gets me a -x, 5x times 3 gets me 15 x's, and -1 times 3 gets me a -3, so that if I combine all this together, I've got a 5x squared, a -x, 15 x's, and a -3, which you can make more simply 5x squared plus 14x minus 3. And all we've done here is kind of redo the same diagram that we had up here with the rectangles, we just did it more simply. Or sometimes we see this as distribution, right? We see this as this foiling that occurs, this distribution where I take whatever this is, some kind of number, and I say I have that many groups of x plus 3. So I should be able to say that I have 5x plus or minus 1, whatever group that is. I should have that many x's in my group, and I should have that many 3's in my group. Oh, that many 3's in my group. And would be plus. So and that many 3's, 5x minus 1. Groups of 3. And if you then say, okay, well then that'd be x groups of 5x and x groups of -1. That would be 5x squared, a -x, and then in the other parentheses that'd be 15 x's and a -3. All in all, again, I think when we simplify this out, we're going to get the exact same thing. So what is it that we're actually looking for in all of this? We're looking for this nice factored form, this 5x minus 1 times x plus 3. All of this over here was just a double check. So we'll kind of section this off over here and say that this right here was just our double check. This up here was an example. And what we're really interested in is when does this entire kind of rectangle equal 0? That's what we're trying to figure out. So let's real quick figure out when that happens. Well, that's going to happen whenever your 5x minus 1 is going to be equal to 0. Because if that whole thing in the front is equal to 0, then everything's 0. And that happens when x is equal to, let's see, 1/5, right? And then you also have when x plus 3 equals 0, the entire thing's going to go. And that would happen when x equals -3. So those are our 2 answers. Now, if that feels weird, we can always go back up to our picture. So for example, let's go back up here to our picture. And let's try plugging in x equals 1/5, and then I'll let you do it for x equals -3. If x equals 1/5, then on the top you've got x plus x plus x plus x plus x. That would be 1/5 plus 1/5 plus 1/5 plus 1/5 plus 1/5. That would be 1. minus 1 groups times, on the other end, you would have 1/5 plus 3, 1/5 plus 3, and sure enough, that would be 0 on the top times anything on the bottom would get us a big fat 0. And similarly, if you do that for negative 3, on the left-hand side, you're going to have x plus 3, which would be negative 3 plus 3, gets me a 0. And on the other side, you're going to have, let's see, negative 3 times 5 would be negative 15, minus 1 would be negative 16, but still 0 times 16 is going to be a big fat 0. So this entire rectangle ceases to exist. It disappears completely when these unknown x's are either 1/5 or negative 3. Okay, so that's pretty interesting that we're able to kind of see how all of these rectangles shift and grow a little bit as we're playing around with different x values. Now, to make my point a little bit more, take a look at this rectangle, and this is exactly what we're playing around with when I'm talking about these rectangles shifting and changing and growing, is that if I make the width super skinny, or if I make the height super skinny, the rectangle ceases to exist. The area goes down to 0. And so we're trying to figure out what x value actually makes that happen. What change in my side length actually causes my rectangle to shift. And to help anchor that down a little bit more, here you can see that rectangle shifting as we put different numbers on each side. So if I have a side of 85 versus, if I have a side of 100, you see how that rectangle starts to creep on down. So as we're putting in different x values, these rectangles are really starting to change to the point where they're disappearing completely. And that's going to happen, well, maybe not on the first step or the second step, but eventually these are all going to shift away. So here's another example of this animation. So let's guess, as we're kind of seeing it creep up, what do you think the number in the bottom right, how many steps is it going to take for this entire thing to disappear completely? Let's watch. It's getting closer, my rectangle's starting to disappear. We can kind of see that height is going down by 2 each time. And after a certain number of steps, that thing's going to go away completely. And this is just one example of how, if you're looking at these rectangles and how they're changing, like imagine I've got this 80 and it's going to be changing, and I've got this 64 that's going to be changing, we can count those x's as things are going away, right? That is the number of steps. So you can imagine this as being like, how many steps, if I'm changing this much each time, is it going to take for this rectangle to disappear completely? So this gives us another platform by which to look at these equations and really give a story behind what's happening. So let's take anyone like this quadratic that we figured out here, and let's figure out the story it's asking. We can rearrange that first set of parentheses to be, I have negative 1 and then plus 5x. And in the second set of parentheses, I have 3 plus x, and I'm trying to figure out when that equals 0. There's a story here. It says that if one of my side lengths is negative 1, and every time I take one step, I am going to grow it by 5, then that's how this width is going to be changing in my rectangle. Versus over here, my height of my rectangle says that I start at a length of 3, and every time I take a step, I go up by that many items. So on my first step, it'll be plus 1. On my second step, it'll be 2 bigger than that 3. So we've kind of got this story here. And the question is how many of these steps does it take for the entire thing to zero out? And now we can really make sense of our answers. In 1/5 of a step, my width will have gone from being a negative 1 up to being 0, right? Because in 1/5 of a step, that'll be where if every step I'm growing up 5, then in 1/5 of a step, I would have only gone up 1, and that would be enough to take my width to 0, where the other side would still have some height playing around with it. It'd be 3 1/5. Or if I give myself if I go 3 steps in the other direction, then what's going to happen with my height is, because my height continues to get bigger and bigger and bigger, we can imagine going the other direction where it gets smaller and smaller and smaller. And that's going to be eventually that logic model that says my height probably came from a 0 at some point 3 steps in the past, whereas my width was probably something that was negative 1 plus or minus 15 big. So it probably had a huge negative side at that moment. There's lots of fun stories that you can put around here to really figure out what it is that we're doing as we're solving through these problems. Okay, excellent. So now let's go ahead and we'll clean this up for our notes, and we'll move on to the next one with this story in our back pocket. Now, do you remember completing the square? Completing the square feels like a very odd mathematical memorization pattern, but actually it comes from dealing with these squares. So let's look here. If I have those 5x squared and I have 14 x's, let's imagine if I was trying to complete that into a square. So the first thing first, I'm looking at those 5x's like I had those up at the top in the orange there, and I'm going, that's going to be pretty difficult to look at it like it's in a square. I can't really organize all of those as if they're in a square. I wish I had just one square. That would be a much easier place to start with. So instead we do a little bit of a thought model here, and we change this over and say, what if instead of looking at this as 5x squares and 14, we look at this as saying I have 5 groups, 5 different rectangles, each one of which is an x squared and has 1/5 as many of these x blocks. No, 1/5 as many of these x blocks. That would be much easier for us to try to turn into a square. Feel kind of weird? Let's play around with that. So let's look. If I have an x squared, that's going to be the one that's right here. Well, we'll hold off on the 5. We can always draw more of these in a little bit. But this 14/5 of an x, well, why don't we just kind of brute force this one? We'll put 7 of those fifths up here. 7, 1, 2, 3. I'm trying to draw them skinny so that they look like they're a fifth as wide, but I'm not going to be able to do that and still have it appear here. So we'll just say that these are 7/5 of my x, half of my 14, 7/5 of them. And I'm going to put 7/5 of them down here. 1, 2, 3, 4, 5, 6, and 7. So this is 7/5 right here, right? 1/5, 2/5, 3/5, 4/5, 5/6, 6/5, and 7/5 of my x's right here. And I would like to make this look into a square. So let's take a look at what I'm missing. Let me make sure I get a different color here. I am missing, if I was going to try to complete a square, I'm missing everything in the bottom right. How much is over there? Well, in the same mentality, we can go through this and say, okay, well, if I have something that is 1/5 long right here and 1/5 long, how big is my little block that's going to fill in this space? And how many of them do I need to go all the way through this bottom right and fill this in? Might sound like a difficult question, but we can do it in the same way that we were doing the rectangles above. If each of these blocks is a 1/5 by 1/5 block, then the inside must be 1/5 times 1/5 would be 1/25. Well, that's no problem. Then we just kind of need to count up how many we have. Because I should have 7 of these 1/5s going sideways. Let's put it in the orange. I have 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, 7/5, and 7/5 going down. Good, so that means inside of here I should have 7 groups going across and 7 groups up and down. That should be 49. I should have 49 of these fifths. That seems much better. So I have 49 of these 25ths here. So I could actually put that in right here. I don't know that I could just like insert that in. I've kind of changed the meaning. So maybe I need to do the same thing I did with those anti-blocks above, and I'll say I'm going to add that in, but to kind of remind myself that I went in debt to do it, I'll put that as a subtraction as well. And then let's look at what we can actually do from this entire expression. I have my 5 on the outside. My first 3 things were what I made from my square, so I can write that as a, let's see, x plus 7/5 square. And then I have my minus 49 over 25. Okay. And then we can come back through and we can always kind of make this simpler here. It would be 5 times x plus 7/5 squared minus whatever 5 times that thing all the way over there is, which would be, oh, there's a 25 on the bottom, so we could just simplify that up. That would be 49 over 5. And there you have it. That's a way that we could look at and say, okay, how was I able to complete the square? Well, what I had to do was I had to introduce a whole bunch of these blue blocks right here. But in order to do that, I had to keep track of the fact that I had some debt that caused. So there was 49 of these blocks that I was keeping in track of in the bottom that were all anti-blocks to help remind me that I was in debt by that amount. And so I just simply said, okay, then I've got 49 of those that are going to be those negative values. And then we looked at this entire thing and said that there were 5 of them going all the way across. This was one of these squares and extra combinations that we created. This right here, square and extra. And if I drew that entire picture again, and again, and again, and again, so that I had 5 of them total, then I would have 5 of these squares and 5 groups of this kind of debt down here. 5 groups of this 49 over 25, which would get you 5 groups of 49 25ths, 5 groups of those got us exactly what I had to make sure I paid back, or what I had kind of taken out as a loan in order to make this whole thing happen. So here's a bit of an animation that's going to walk us through this. So again, we look at this as if we have 10 of these x squares that we're going to try to factor out. But why not look at that as just saying I have one of these x squares that I'm going to start with, and then we'll multiply by 10 later. So we say, okay, what do I have? Let's split that apart and start to make it into a square. I have half of my middle term, half of that 16 here in this case. And I say, what do I need to complete my square? Well, what I need is whatever the -8 and -8 here would get me, that's 64. And I accumulate some debt that I kind of keep track of off to the side. So I'm able to rewrite my equation in the form of a square, and then I just talk about how many would be if I had 10 of these at the very end. You can ignore the vertex form there. So again, let's watch through and see what happens. We're going to try to say I have 10 of these situations, but I only need to talk about one. So let's factor it out and just talk about what each of these combinations look like. And I've got some things here. We're going to split it up in half, and then we're going to make a square out of it. So we're literally dividing it by 2, and then we're about to make a square here. Now, you can't just create something like this. You had to actually balance it out to remind ourselves that we went into debt to do that. So that's where that -64 kind of creeped away. And so we just kind of keep track of the mathematics from this standpoint and say we went through all of this effort to say, now I have a square, I have a bunch of debt that I collected, and I can look at that as saying, okay, well, what does each of these 10, after I look at this in 10 different situations, how can I kind of distribute those numbers out? Now, we talked through a way of solving these things called the quadratic formula, and if you go back in that lecture and watch it, the quadratic formula is actually solving things by completing the square, believe it or not. So just like if I wanted to try to solve this one out, I'll show you in a moment. What we can do, if we wanted to do it by completing the squares, we could actually pick up right where we left off, which was saying that this entire thing right here is equal to 5x plus 7/5 squared. And then we would say, okay, minus 49/5. That was this part right here. And we'll put in a little -3 there as well in this situation, okay? So this is the exact same idea. I'm just starting with where we picked up in the last problem. 5 groups of x plus 7/5 squares, and then minus, let's see, this -3 could be thought of as -15 over 5. So we'll write that in, 49 over 5 minus 15 over 5, which we could then write more simply as saying 5 times x plus 7/5 squares minus, and that would be what, 64/5. And we're trying to figure out when this entire situation equals 0. Well, we could just run on through this entire thing and say, okay, no problem. We're going to try to get that x alone. We're going to get the positive 64 over 5 on the other side, which leaves us with a 5 and an x plus 7/5 square. We could then try to get rid of the 5 on both sides. We divide both sides by 5. That's going to give me x plus 7/5 squared. And to divide this fraction by 5 means to put another 5 on the denominator, so that would be 25 on the denominator and 64 on the top. We would square root both sides. That would get me x plus 7/5, oh, not square root, plus or minus square root both sides, plus or minus square root the 64 and the 25, which we could then write even more simply as saying that is going to be a plus or minus square root of 64 would be 8, and square root of 25 would be 5, so plus or minus 8/5. And then we would want to, let's see, subtract the 7/5 from both sides. So we would say x is equal to -7/5 plus or minus 8/5, which we could write more simply as just saying -7 plus or minus 8 over 5. Okay, so this would be our two answers right here. Now, the quadratic formula is one that we've kind of known as a shortcut, and I'm going to show you that they're the exact same thing, because the quadratic formula is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So let's take a look at what happens through this one. This would be what x equals when the situation above is true. That would be x equals, opposite of b would be negative, and b would be that 14. So negative 14 plus or minus the square root of b squared, that'd be 14 squared, minus 4 times a times c would be times 5 times negative 3, all over 2a, and 2a would be 2 times that 5, okay? So then we're going to work this entire thing through. We're going to see what we get. Negative 14 plus or minus the square root 14 squared. Let's go ahead and throw that into our calculator. So it's going to be, what, 14 times 14 gets me 196. Minus 4 times 5 times negative 3. 4 times 5 is 20. Times negative 3 gets me negative 60. A negative 60 would be a positive 60. And then at the bottom, you're going to have a 10. And that would get us, let's see, negative 14 plus or minus 196 plus 60 gets us this 256, which I think we can square root to get 16. Very nice. So plus or minus 16 divided by 10. And is equal to, let's see, I think we can simplify this out by recognizing that on the top you have a, that's really, all of this is two groups of negative 7 plus or minus 8 divided by two groups of 5. And sure enough, if you take away those 2's, you're left with negative 7 plus or minus 8 over 5. So we have the exact same thing, and in fact you might have seen some parallels as we were going through this entire thing for how the quadratic formula was solved. If not, then go back and watch the lecture on how we created this quadratic formula, and we actually created it by completing the square. It's the same exact thing. Okay, so now we're going to be talking about ways that we can graph this, because graphing it gives us a lot of our solutions depending on like how big are these rectangles, right? Those are the outputs of this entire equation. How big are the rectangles after we've taken these steps to either side? And sometimes it's going to be easiest for us to talk about these graphs not as all of the points, but by their kind of important, most distinguishable points. The first of which is the vertex, and if you want to recognize that in your picture, that's this part right here. For quadratics that open upwards, like this U shape, the vertex will be the lowest point. But if I flip this entire thing, like we have seen before, if I was to make it negative, or I wanted to look at negative squares and they keep getting more negative area, the vertex would be the highest point. It'd be kind of like a U that was flipped upside down. In other words, like kind of this upside down cup shape. Let's see, the axis of symmetry, we can break apart what this is. Axis, like our y-axis and x-axis, is just a reference line. And symmetry, we're looking for when something is the same on either side. So that would be what this part right here is, this dotted line. This would be our axis of symmetry. I could look for our y-intercept. That's going to be the exact same thing that we have always talked about. So y-intercept is going to be the y value I have when I'm crossing the y-axis. The x-intercepts are going to be here and here. And notice it calls them real zeros. I wonder why that is. Well, if we think back about our story, whatever x value this is, like 3, says that I'm taking 3 steps in changing my rectangle, or I've adjusted my rectangle by 3. What does that get me as my size of my rectangle? And we would plot this point here, and we say, okay, well that point would be 3, 0. In other words, saying that if I adjusted it by 3, my area, my rectangle, is now 0. So these are the locations where my rectangle ceases to exist, are over here at my x-intercepts. So that's why we would like to pay attention to where those are. They're kind of these cutoff lines from when I start to switch between negative rectangles and positive rectangles. So those will be our x-intercepts. And notice there can be 2 x-intercepts. But if I was to shift this up so that it just barely touched right here, there would only be 1 x-intercept. I could even shift it up even more where there was no x-intercept. So there's not always going to be an x-intercept, and there's not always going to be 2 x-intercepts. It could be either no x-intercepts, 1 x-intercept, or 2 x-intercepts, depending on how far we shift this graph up and down. And that's just simply saying that imagine that you have some kind of rectangle, and I wanted to add, I don't know, 5 to it. Well, now that's going to be 5 bigger than my rectangle, so maybe my rectangle only becomes so small. Then adding 5 to it would keep it from ever becoming 0. That feels like an easy or a difficult example. Let's do it like this. Let's take the rectangle we were just playing with when we were drawing it up at the top here. So that would be this one right here. this rectangle right here that we said could kind of change its shape a little bit back and forth. And let's say that maybe I wanted to say I was going to add 5,000 of those little unit blocks into my total shape. Do we think that would ever make it disappear? Even if the rectangle disappeared, I'd still have 5,000 unit blocks. So that's kind of what's happening when we're shifting our pictures up, is we're saying, what do all of these blocks together get me for area? Do they ever disappear entirely? Sometimes they will. Sometimes they'll disappear only for a moment and then they'll grow back. Sometimes they will disappear, come back as negative values, and then kind of come back to small again and then shift back towards positive values. We get a whole bunch of fun little plays. We'll get to see some examples of that. Okay, good. The domain and range, let's keep in mind what that means. Domain are all of my valid inputs. So these would be valid inputs into this storyline. But there's a lot of valid inputs into this storyline. Like if I said, how many times am I going to change or shift this rectangle? I could make negative shifts. I could go backwards in my kind of animation. I could go forwards in my animation. For parabolas like this, your valid inputs are all real numbers, because there's no reason why I can't keep shifting my rectangle by changing its width and length, or counting how many width and length changes I've done in numbers. So that's always going to be fine. Your range, the range is a little bit more tricky. Just like with the animations we were looking for, we're looking for the smallest size this rectangle could ever be. So it'd be the smallest size all the way up to the largest size, which if we look in our picture up here, looks like the smallest size would be how far down it gets in my y-axis, because my y-axis, after all, is all my answers to the question of what's the size of my rectangle. And it could go as high as it looks like forever. So depending on the picture, we'll be able to pull out all of the possible area sizes of these quadratics and all of the possible steps that I could go either in growing my rectangle or shrinking it back down. Okay, so let's try to connect a whole bunch of these, but we're going to try to use some of the ones that we've looked at before. So again, explain how the corresponding rectangle diagrams support everything. Well, if in this equation that we just dealt with right here, what's the rectangle diagram? So here's a rectangle diagram. What was our completing the square? Our completing the square so that I could actually look at this entire thing as saying that I have 5 of these squares, each of which was x squared plus, let's see, so 5x plus 7/5 squares. So let's look at what the picture for that is. That's 5 of these things that were x plus 7/5 by x plus 7/5, and that got us, let's see, 7 little units here, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then in here we had a whole bunch of, we had 49 little unit blocks that all appeared in here. And then we had that 5 times. Here was our first square, here was our second square, here was our third square, here was our fourth square, and here was our 5th square. We'll put it up here. And in each of these, it was the exact same picture. I said that I had this, a whole bunch of these little 1/5 blocks that I had to put over here, and a whole bunch of these unit blocks to make it into a nice perfect square. And then we did it for this one. We did it for this one. And we did it for this one up here. Now we weren't able to just create all these squares. We had also amassed some debt to do that. We had this many kind of unit blocks that we had to kind of amass over here in a pile. And I'll just kind of draw those willy-nilly. This was your debt pile right here. We had to kind of amass as we were playing around with this. And then up here were our 5 squares that we had created after kind of taking out that loan of some unit blocks. No problem. All right, what about the graph? How could we graph this entire thing out? Well, maybe we'll start off with just how we graph anything, table of values, and we'll see how it all connects. So let's do a table of values. Maybe I'll look at -1, I'll look at 1, let's do 0, let's do 1, let's do 2, and let's do 3. And we're gonna plug that into here each and every time. So the first thing I'm gonna do is 5 times -1 squared plus 14 times -1 times negative or minus 3. There we go. Let's move all this over a little bit. Okay, and so I can go ahead and solve this entire thing out. Let's see, negative 1 squared would be positive 1 times 5 is 5. Minus 14 gets me a positive, or negative 9. Minus 3 gets me negative 12. So this right here would be a negative 12 that happens after I ask about the question of x being negative 1. What if I put in 0? That'd be 5 times 0 squared plus 14 times 0 minus 3. And so that would be, let's see, 5 times 0 is 0, plus 14 times 0 is 0, minus 3 would be equal to negative 3. For 1, that would be 5 times 1 squared plus 14 times 1 minus 3. And let's see, again, 5 times 1 squared would be 5, plus 14 would be 19, minus 3 would be negative, let's see, 5 times 1 would be 5, plus 14 would be 19, minus 3 would be negative 6, or it would be a positive 16. Okay, good. And then for 2, I believe this is going to grow even faster. So we actually have 5 times 2 squared plus 14 times 2 minus 3 would be equal to, 5 times 2 would be 20, plus 28 would be 48, minus 3 would be 45. Okay, so this is actually going to be quite the challenging picture to plot over here in my graph, because that means that when I am going over to negative 1, I need to go down to negative 12. That's a way off of my scale. At 0, I can go to negative 3. That works out pretty good. So here is mine right here. And then after that, I go over to 1, and that's going to jump all the way up to 16. Okay, that seems pretty huge. How would I exactly graph this entire thing? Maybe I'll change the scale. Let's change the scale. We'll use it as we will here. So let's make this from negative 1 to negative 10, negative 20, negative 30, negative 40, negative 50, negative 60. No, I needed to change the other one because my y values were the big ones. Let's go back through here. I'm going to make this so I have negative 20, negative 30, negative 40, negative 50, negative 60. And up here I'll have 10, 20, 30, 40, 50, and 60. There we go. Let's play around with this and try to sketch it out. All right, we'll do it in a different color. Let's make it into blue. And I'll say, okay, so at negative 1, I need to go to negative 12. No problem. Negative 1 brings me down to negative 12, which is right about here. Good. And then I need to go 0, negative 3 is 0, negative 3 would be right about here. And then I would say, okay, at 1, I need to go up to 16. 1 and 16 would be right about here. And then after that, I would go to 2 and 45. 2 and 45 would be right about here. Okay, so I've kind of got a little bit of that U shape. It looks like maybe there's going to be more happening over here in my negative direction. So let's adjust my table, expand it out towards the negative direction. We'll try it with negative 2. That would be 5 times negative 2 squared plus 14 times negative 2 minus 3 would be what? Negative 2 squared would be positive 4 times 5 would be 20, minus 28 would be negative 8, minus 3 would be negative 11. Okay, so at negative 2, I need to go to negative 11. That's going to be right about here. And then I could do one for negative 3. Negative 3 would be 5 times negative 3 squared plus 14 times negative 3 minus 3 would get us, let's see, negative 3 times negative 3 would be 9. Times 5 would be 45, minus 42, and then minus 3 would be 0. Okay, it would be 0. Oh, well, that actually works out quite nicely. Wait a second, we've seen that one before. Where did we see that? Where did we see that? Let's go back through. Where did we play with that one before? Right here. Look right here. There's that negative 3 again. Oh, and that makes sense because that x value of negative 3 was when I was going to get a 0 with that original rectangle. Oh, son of a gun. So that actually could have been a faster way for us to have plotted this entire thing, is I could have just plotted the place where I had a 0 here at the negative 3, and I'm guessing I would have had a 0 here at this negative 1, or at this positive 1/5 mark, and that would have been a much faster way for me to just kind of have done a nice little parabola. So we've discovered something. Now, where's the lowest point? That's my question. Since there's an axis of symmetry, shouldn't there be a situation where I have, like, shouldn't this be symmetric going right down the middle? Like, shouldn't I just be able to find out where the middle is between these points? Like, for example, if my 0 is here on the 1/5 and my 0 is here at the -3, shouldn't I just be going to the middle to find out where that axis is? Let's play around. Where would that be? That would be -3, and then I'd be trying to average it with that 1/5, so I'd try to be adding it to that 1/5. That would get me, -15 over 5 plus 1/5 would be equal to -14/5. Oh no, because I didn't average it at any point, did I? I needed to actually have divided this entire thing by 2, right? Okay, so I'm adding them together and I'm kind of dividing by 2 to get that average. So I need to take this whole thing and divide it by 2, which means I have to take this whole thing and divide it by 2. So that should get us, let's see, -7/5. -7/5. Where have I seen -7/5 before? After all, I mean, that makes more sense. -7/5 would be a little bit further over than -1. That looks right about here. Where have I seen 7? I've seen 7/5 right here. Oh, that's crazy. So we're starting to discover some things for how I could have graphed this faster. I could have just grabbed the 7/5 from up here, and that probably would have been the place where I could have drawn my axis of symmetry. Well, how far down does my parabola go? Like, what's the lowest point? Let's try plugging that in. I mean, it's going to happen when x is -7/5, so let's just try plugging that in. So now we're going to go through. It's going to require a little bit of calculator work, but I think if we keep it as fractions, it'll be a little bit easier. So let's go through and we'll do this. We'll say, I'm going to now, in my table of values here, I'm going to try -7/5. I'm going to try to plug that in. So I've got -7/5. We're going to put that in as 5 times -7/5 squared plus 14 times -7/5 minus 3, which should be, let's see, 5 times -7, that'd be equals 5 times all this stuff squared, -7 times -7 would be positive 49, 5 times 5 would be 25, plus, let's see, 14, I'll put a little times here, 14 times -7 over 5 minus 3, we're going to need to do a lot of common denominator work. Oh, but maybe not too much, because here I've got 5 and the 25 will kind of simplify out a little bit, so this is really 49/5. On the next one, you've got 14 times -7. What does that get us? That gets us 14 times -7 gets us -98. So I can put that right here. I have -98/5. And I probably want to make this 3 into fifths as well. That'd be -15/5. So all in all, what would that get us? That would get us, let's see, 49 plus, or minus, -98, or minus 98, there we go, minus 15 should have got us -64/5, right? Wait, I've seen this before too. Where have I seen -64/5? And lo and behold, -64/5. Okay, so now we figured out some really interesting shortcuts just by playing around. If I can write things in this structure of completing the square, then I can recognize where my vertex is. It's going to be the opposite of the number on the inside, and then the regular of the number right here, which I think should make sense from our composition of functions lecture, or our adjustment of functions lecture. After all, if I add something to the x, doesn't that mean that I'm shifting everything over in my coordinate plane? And if I subtract something after all of that, doesn't that mean I'm dropping it down? So it makes sense that I took my parabola and kind of shifted it over to the left before dropping that vertex down to its final location. So I'm okay with that that helps me kind of gut check it out a little bit there. And also, we're just kind of seeing that those numbers pop up very nicely. And we also recognize that if I had it in my factored form being that, let's see, I'll write it over here, the factored form being this 5x minus 1 and this x plus 3, that this factored form of 5x minus 1 and x plus 3 was used to figure out where those zeros were. And those zeros happened when x was equal to -3 and x was equal to 1/5. Lo and behold, that's exactly where we had the zeros on the graph. So now we can see why it is that we've been stressing all of these different methods. We can use whatever information we have available to us in a variety of different patterns to be able to graph the parabola quickly and get answers not only for certain questions, but for all questions. We're able to create a picture that's worth 1,000 words. Okay, so let's come down here and do a little bit of capturing here. A quadratic function is in vertex form if it is written as, okay, so vertex form, that was the one that we were able to determine the vertex from. That was like this one right here. Okay, so we're going to try to talk about this one in a little bit more abstract terms. So it's going to be written in f of x equals a times x minus h. Let's use the same notation we did when we were talking about transforming functions. So a times x minus h squared, let's see, plus k, right? And the graph of the parabola has the vertex. Where was that? If we come back up here to our example again, it was going to be at the opposite of the number in the parentheses, and exactly for the x value, and on the y value is going to be the number outside the parentheses. So let's try to capture that. So it has a vertex at the opposite of the thing in the parentheses, so that would be plus h, and the same thing as the one on the outside, h and k. There you have it. Now the parabola opens upwards, just like the one we have up there, if what? Let's take a look. We had kind of growing values that were occurring. As I was looking higher and higher, these numbers in the front here started to get really, really big, whether it was positive or negatives going in. These were the numbers that made it really, really big, and these were not being flipped at all. I think this first number is what determines if we go up or down at all. And so we'll say it opens up if this a value is greater than 0, if it's a positive number. And again, this should remind us of our transformation of functions discussion of saying if I'm multiplying something by a number, it just means I'm stretching it vertically. And the parabola opens downwards if this a value in front is less than 0. Okay, so now you try along with that. There's a lot that's going on here, but I've given you a vertex form of a quadratic function. So you should have a lot of information here to grab your vertex. See if you can find out what the coordinates are of that vertex. You should be able to pull them out of the structure up here. Keep in mind, you need to be a little bit careful because like when you're looking for this x, this h value, it's going to need to be attached to if it says negative h, you're just gonna be pulling out the h value. In other words, the opposite of the things inside the parentheses. Your k, however, is what we're going to be leaving alone. Okay, does it open up or down? You should be able to determine that by what's being multiplied on the outside of the parentheses. What is the equation of the axis of symmetry? Well, the axis of symmetry should be a vertical line that is occurring going right through the vertex. And so it's going to be something of the form x equals whatever. Like for example, if we want to come up here, this one right here was x equals negative 7/5. That's where our green line was x equals negative 7/5. You could draw that in if you want. X equals negative 7/5. Good. What else do we have? Find the y-intercept. Well, or find the x-intercepts. This is going to be when you're trying to set this entire thing equal to 0. So you could actually just start that off by saying negative times, or x minus 2 squared minus 4 equals 0, and solving that on down to get two different x values. Wherever those x values are going to be two places where you plot it on your graph, and then you're going to say, okay, between those I'm going to get some kind of, it's going to go through my vertex, and then it's going to pass through these, and I'm going to get my nice little u-shape. Find the y-intercept. Remember, the y-intercept is simple because this is going to be when x equals 0, what happens at y, and that's going to be wherever this thing crosses the x-axis or the y-axis. So I guess I should draw my example here a little bit like it's got both things we're looking for. Here you go, right here. And we'll adjust my line of symmetry because that needs to make it actually look symmetric. Good. So now we get our y-axis. This happens when x is equal to 0. Let's see, we have our x-intercepts. That happens when y is equal to 0. That's why we set it equal to 0. Sketch the graph. You can do that off to the side and state the domain and range. We should already know that the domain should have no problem at all. There's nothing that's going to give me trouble. If I try to subtract 2 from it, square it, make it negative, I can do all those things. But my range, I'm going to have a lowest value and a highest value. See if you can figure out what those are.